Hello, Year 11 Triple. Last lesson we had a look at the difference between elastic and inelastic collisions. Now, collisions that are purely elastic, what happens is not only momentum, but all kinetic energy is conserved. There's no loss at either end before or after the collision. Now, purely elastic collisions are very few and far between. We're going to be looking at one today that involves a sort of slingshot where a space probe moves round the orbital path of a planet and gets an acceleration kick as a result of that elastic collision. Now, most collisions are inelastic. Momentum is conserved. Momentum before the event equals the momentum after the event. But in inelastic collisions, you are going to get some kinetic energy lost. It's going to be transferred into sound and heat and possibly even light. I'll give you an example. I'm taking my hands now. Some of that kinetic energy was converted into sound and heat when my hands came together. Now, we're going to move on. You will need a calculator today. The graph shows the motion of a car travelling at 15 meters a second. Is quite happy in this section here. Unfortunately, that car then hits a wall, and so it slows down, temporarily stopping and then rebounding off the wall in an opposite direction. So we have a negative velocity value here before it gently rolls to a complete stop some way away from the wall. I hope that you understand this the start of this question. So question 8. How can you tell from the graph that the car is pushed backwards? The velocity has a negative value. Okay. Write down B part 1. Write down the duration of the collision. Well, the collision starts here and ends here, and so that value there is 0.2 seconds. So So 0.2 seconds is the collision time. Now, question 2, calculate the change in velocity, okay, caused by the collision with the wall. It started off at 15 meters a second, yes? It then ended up at moving away at 5 meters a second, but in the opposite direction. So the total change is those two values added together, which is 20 meters per second. We started here and it ended up going all the way down to this point here. So there's your change is in there, okay? 20 meters a second. Now, part 3. Working out the force. Force equals the change in momentum divided by the time it took So the momentum at the start was mass times velocity. The mass of the car was, it does say in the question, I'm trying to find it, 1200 kilograms. So mass times the initial velocity, which was 15. Take that away from the mass, which didn't change, we're assuming. Remember, it's -5, so a negative plus a negative is going to come up to a plus. So we get 18,000 this side. Take away a -6,000. Minus and a minus becomes a plus. That's divided by time. This is also divided by time. And that equals 24,000 kilogram meters per second. That's the change in momentum divided by the time it took, 0.2, and we get a value there of 120,000 newtons, which you could write down as 120 kilonewtons if you so wished. Now then, estimate the distance that the car rebounds. Remember, what we're looking at here is the area of the triangle, and the area of triangle is half times the base times the height, and that equals 0.5. That equals 0.5 times by the base, which is from here to here, so that's 1.8 multiplied by the height, which is 5. So the base of it was 1.8 times it by the height, which was 5. And so it rebounds 4.5 meters. Okay. Now, D, name a safety feature in a modern car. I'd be looking at seat belts or an airbag. And what happens is, the science behind it is as follows. The change in momentum. You don't want the change in momentum occurring very quickly. That increases the forces on the occupant. So you want the change in momentum, you want the person slowing down over a longer period. So change in momentum occurs over a longer time frame. It provides a cushioning effect and reduces the forces on the occupants so they don't get as damaged. Okay, a gun fires a bullet of mass 0.01 kilograms at 1,000 meters a second. It goes through the target and slows down. It has the same mass, but it slows down to 100 meters per second. A, calculate the change in momentum. Nice and easy. If we say that this is number 1 and this is 2, A1. Number 1, what's the momentum there? Equation. Workings. Answer with the right units. For 2, equation, same mass, less velocity, change in momentum. Change in momentum equals 10 take away 1, which is 9 kilogram meters a second in that direction. Okay, happy with that so far? Great. Then it says, I'll do this in a different colour. Let's have a look at section 2, right? Calculate the mean force. Well, we've already been given the equation. Force is change in momentum divided by the time it took. The change in momentum was 9. The time was 0.0005 seconds, and that gives us a mean force exerted by the target on the bullet of 18,000 newtons or 18 kilonewtons. B part 1. Calculate the total kinetic energy released by the bullet. Okay, you've got some information here. You could use this to work out the momentum of the gun and therefore the bullet, but we got all the information that we need anyway. Kinetic energy equals a half times the mass times the velocity squared. The kinetic energy of the bullet is 0.5 times its mass, 0.01, times by its initial velocity squared. Notice how I'm putting brackets around 1,000 so I'm not getting confused. And we get the answer 5,000 joules. Okay? Now, this is a tricksy one. Explain why, when an explosion occurs, the smallest fragments travel the furthest. Well, momentum is mass times velocity, yes? If the momentum stays the same and you've got small mass, so small fragments, then you are going to have high velocity, okay? So if momentum is conserved, if the object has a small mass, then it's going to have a very high velocity. Now, why do those objects cause the most amount of damage? Because kinetic energy is a half mv squared. So if you've got a high velocity and you square it, you are going to get an enormous amount of kinetic energy, which can then be transferred to damage or injure the person, unfortunately. Now, question 7. 2 trucks, A and B, each have a mass of 5,000 kilograms, and they collide with each other. Now, state the law of the conservation of momentum. Well, we know that momentum before an event equals the momentum after the event. And then, so that's that bit. Then we want to calculate the velocity of truck B after the collision, after it. So here we go. I'm going to do this over here. Let's have a look at the momentum before. Okay, so for A, for truck A, this one here, its momentum equals mass times velocity, which is 5,000 kilograms, multiplied by its velocity, 5, and that equals 25,000 kilogram meters a second. Let's do exactly the same for B. That is moving as well. M times V. But of course it is moving in exactly the opposite direction, so this is, we're going to give this a negative value, so it's minus 5,000 times 2, which gives us minus 10,000 kilogram meters per second. Now, if we want to know the momentum, the total momentum before the event, we add these two values together. So total momentum before crash equals 25, add a negative value, which gives us 15,000 kilogram meters per second. Okay. Now, let's have a look at the momentum after. We can work it out for this, no problem at all. So A had a momentum of m times v, which is 5,000 kilograms multiplied by its velocity, which is 1, gives us 5,000 kilogram meters per second. Okay. Now, momentum before must equal the momentum after. We know the momentum before was 15,000. The momentum after, we've worked out part of it was 5,000. So the conservation of momentum, the law is momentum before equals the momentum after. So we've now got to work out the momentum of this truck here, which is pretty simple. B, its momentum must be 15,000. Take away the 5,000, gives us its momentum must be 10,000 kilogram meters per second. Because momentum before the event is that, and the momentum after the event will be the same. So it's that plus that comes back to this. Now what we can do is work out the velocity of this truck here, because we know that P equals mv. Put v on its own, it equals P divided by m, and we know its momentum is 10,000. Divide that by its mass, 5,000, and that gives us a velocity of 2 meters per second. Whoa, that's quite a heavy question, that is, I've got to say. Ooh. Now I'm going to have a look at this question here. I'm going to do that over here. So, doing a different colour, I think. So, we are looking at forces. Force equals change in momentum divided by time. So we're looking at truck A. Now truck A had a mass of 5,000 at the start and a velocity of 5. So that's its momentum at the start. And then we take away its momentum after the collision, and it was still the same mass, 5,000, but it was now only moving at 1 meter a second in the same direction. So there's the change, and we divide that by the time that it took, and it was 0.4 seconds collision time. And so we get 25,000 take away 5,000 divided by 0.4, and that gives us 20,000 divided by 0.4, and that gives us 50,000 newtons of force, which equals 50 kilonewtons. B part 1. Calculate the kinetic energy lost by truck A during the collision. Before the collision, the kinetic energy equals a half mv squared, and that equals 0.5 times its mass, which was 5,000, multiplied by 5 squared. And that gives us a value of 62,500 joules is the units for kinetic energy. Afterwards, kinetic energy equals, it's the same equation, same mass, different speed, 1 squared, and that gives us 2,500 joules. So kinetic energy lost equals 62,500, take away 2,500, gives us 60,000 joules of kinetic energy was transferred. It was lost, it was transferred as heat and sound. Okay, obviously an inelastic collision. Have a read through this question. I'm going to go through the answers. A. Calculate the velocity of the space probe as it moves away from the planet. It is now moving at v plus 2u, and that equals 20,000 plus 2 lots of 15,000, and that will give us 50,000 meters per second. Now B part 1, the kinetic energy is a half times mv squared. That's exactly the same equation as that. And that equals 0.5 times its mass, 100 kilograms, multiplied by this new top velocity, squared of course. And that gives us 1.25 times 10 to the power of 11 joules. Now, question B, part 2. Explain how the conservation of energy applies in a slingshot orbit. Well, the momentum before the event must equal the momentum after the event, yes? Now, the masses do not change. The space probe hasn't gained any mass. The planet hasn't lost any mass. So what we've got is a situation where the velocity of the probe, the space probe, has increased, whereas the velocity of the planet will decrease, but by a tiny amount due to its enormous mass. So yes, the space probe speeds up considerably. The planet does slow down, but by an absolutely tiny fraction, because remember, momentum is mass times velocity. Okay. And finally now, momentum, this is C part 1, before the event, we're after the momentum. of the probe. Mass times velocity, and at the start it was 100 kilograms multiplied by its original speed, and that gives us 2 million kilogram meters per second. After the event, momentum is mass times velocity, same mass, bigger velocity now, 5 million kilogram meters per second, and so calculate the change in momentum. It will be this, take away this, so change in momentum will be 3 million kilogram meters per second. Now, that's the end of the lesson. Quite a heavy maths lesson this. If there's any concerns, do let me know. Not afraid to go through the answers again in a slightly different way if necessary. Have a read through that as well. Such slingshot orbits are really elastic collisions where the objects involved never hit each other, but they are affected by the gravitational pull as they approach one another.